I'm assuming everybody can see my slides at the moment. So thank you very much, Yanis, for inviting me. Of course, it's a great pleasure. And I remember when we first met at IBM Almaden, you were an intern and I was a postdoc. So that was really a very nice time. So data profiling, this is an area that I've been working on for quite a while. Data profiling is about collecting metadata from, let's say, an unknown or new data set. So how did I get started? This was also a long time ago at CIDR 2005. This was a time when websites still looked like this. We had a paper there about, let's say, automatic information integration. And we were trying to integrate life sciences databases. And how do you integrate them? We were looking for ways to join them up, right? And how do you join things? You look for inclusion dependencies across data sources so that these are hints of how to combine the sources, and then you can go on and do entity resolution and all the other nice data integration topics. And this topic actually has not gone away at all. This is a selection of the posters or the postcards maybe for EDBT, and all of these have something to do with metadata and need a collection of metadata. I'm highlighting this one here, a talk yesterday about data lakes, and you can see no schema, huge tables. Existing techniques are not applicable for whatever problem they're solving, but I would also say no metadata to even get started. And this is a typical problem. Here you can see this broad, let's say, pipeline. You have all sorts of data sources. You need to do some kind of a data preparation, including cleaning, integration, feature engineering, all these things to then serve the applications on the right-hand side, like knowledge discovery, analytics, AI systems, etc. So this is a typical pipeline. And my argument will be that if you do some data profiling in advance, extracting all kinds of dependencies from the data set that you've just gotten, you can improve lots of the things that you're doing, both in the data preparation area and in the application area. And as we go through these slides, I will always have a few open research questions there in the top corner, and we'll be talking about those briefly throughout the talk. So, but to convince you that data profiling is important and that we do need metadata, I'll show you two very quick use cases for the kinds of metadata we're interested in. So we're at the moment writing a survey where we're looking at optimization techniques, query optimization techniques using unique column combinations or key candidates, functional dependencies, order dependencies, inclusion dependencies. How can we use those kind of things to improve our query plans or query processing time? You're not supposed to read this table, but I'll just give you one quick highlight, a very obvious one. Suppose you have a select from a group by query and you're grouping by A and B, and you know that A functionally determines B, then of course it's sufficient to group only by A, and the database system will be happy. It will, maybe have a more efficient plan to execute that shorter query. And there are many, many opportunities for optimization. And I would claim that not much of them have actually made it into commercial or, let's say, viable database management systems. So I think there's a big opportunity here. Why is it difficult? We'll talk about that later. The problem will be, how do I maintain that metadata as the data evolves? A second use case I'd like to highlight, which is that of data cleansing, is very typical for commercial data profiling applications. So any data profiling tool that you have a look at will probably be bundled with a data quality or data cleansing suite of that company. And the thinking here is that you discover approximate dependencies, so the dependencies that are almost true. And then if you have a closer look at them and you say, actually, this thing should be true all the time, you have a data quality problem, you go ahead and detect those records or values that violate that dependency, and then you can clean them, right? That's a very typical approach. I want to show one really nice example from a paper by Shuchu and Ihab, Ilias and Paolo Papati about holistic data cleaning, just to give you a highlight of what kind of things you can be doing. So their proposal was, well, if we have some functional dependency violations, like here, zip code should determine the state, but there's a violation here, and any of those 4 values could be the culprit. And then you might have a denial constraint. So somebody earning a lower salary, even though that person is at a higher level, and you could say that's a violation. And if you look at all these violations together, you can try to figure out where should I correct. And in this case, quite likely the state of the first record is wrong, because if you correct that to New York, all the violations go away at once. Right? So again, you need to know these dependencies to then clean the data. Okay, so now let's look a little bit closer of how do I get these this metadata. You can do something very simple, right? You get a new CSV file. In this case, this is North Carolina voter data, very popular data set. You open it up in Excel, let's see, and you can do a little bit of profiling right away. So you can count the number of columns and you can look at the column labels. And then as a computer scientist, what I would usually do is scroll to the bottom and see how many rows do I have. That's a little bit of metadata. And then Excel has this nice feature of zooming out, so you can maybe recognize some patterns in the data. In this case, maybe, if values are missing in one column, they'll also be missing in a whole bunch of other columns. That's already kind of a, let's say, missing value dependency that you could visually see here. There's not much research in this particular area, so that's one of my open research questions. Can I support visual data profiling, right? How can visual analytics help me understand properties of my data in this very basic form? Okay, this is very simple. We want to go beyond what Excel can do, right? So let's have a look at the more, let's say, interesting data profiling tasks. So Ted Johnson of AT&T gives a quick definition in the encyclopedia. Data profiling refers to the activity of creating small but informative summaries of a database, right? Okay, so what could that be? There are a whole bunch of tasks that work on an individual column. These are basically counting tasks, right? How many distinct values do I have? How unique is my column? Are there any specific patterns, distributions, histograms about my data? What is a little bit more interesting, or much more interesting if you ask me, are those multi-column tasks where I look for properties that hold over combinations of columns. Why are they more interesting? They're more expressive, and they're also more difficult to discover. So we're looking for key candidates, we're looking for inclusion dependencies, for functional dependencies, for order dependencies, for denial constraints, et cetera, all these nice complicated beasts that we would like to know about and then drive our applications later on. Okay, so this is what we want to do. Why is this difficult? Well, you can see in this slide, so we're very used to the scalability in the number of rows, right? So this is what we database people do all the time. But here we also need to be scalable in the number of columns, in the sense that we're looking at column combinations. And the keyword combination already raises an alarm bell here, right? Because it's exponential in size. So if you have a table of 100 columns, you're already looking at 1.3 nonillion column combinations if you want to go through that space, let's say, to look for key candidates, right? And clearly, that's not what we want to do. We want to find some more intelligent algorithms that do this much faster than this naive approach. And what is worse, though, is that the solution space is also very large. In principle, there could be an exponential number of functional dependencies or also key candidates in any given table. So that's already quite bad, but nevertheless, we can get there. An interesting research question, open as far as I know, is can we somehow predict the problem and solution size for a given data set? So can we make use of known properties of the data to do some pruning or to understand how complicated will it be to discover? Because of course, these extreme cases are not very realistic. Real values or real databases have much nicer distributions, which is why our algorithms work much faster than we would predict in a naive way, and why actually the number of dependencies is also not usually exponential. Okay, so this is the problem statement. My agenda for today are these points. We'll start very simple with some basic statistics, just to show you that there's also a little bit of fun to be had there. And then we'll go through, let's say, these three very canonical dependencies that we're interested in: unique column combinations, functional dependencies, inclusion dependencies. Of course, there's a whole bunch more. There's a lot of research, and I will only be able to cover a little bit. And what I'm trying to do in this talk is just give some, let's say, algorithmic intuitions and insights here. So this is going to be, a little bit shallow to get you excited about this research topic, hopefully. Okay, so if you're looking at single column things, an obvious profiling task would be, can I understand the data type, right? Can I distinguish strings from numbers? Can I extract SQL data types? Or better yet, can I extract semantic data types? Can I understand this is a phone number, this is a zip code, and this is a last name, right? So you could call this a profiling task because we're trying to find metadata about our data. And as I said earlier, you can do a whole bunch of counting, number of rows, average value length, these kind of things, and then histograms and other distributions that we might be interested in. Right? An open research question here that we're trying to look at the moment is, can we find useful regular expressions for data columns? Right? It's an obvious thing. What is a good, the point here being good regular expression to describe all the data? It cannot be too general and it cannot be too specific. This is a good research topic, I think, to work on. One very quick highlight, you can see the very last point at the bottom right is the first digit distribution. So I just want to show one slide because I love this kind of fact. Some of you might know this, or maybe even many of you. So just very briefly, there's a thing called Benford's law frequency, or the first digit law, discovered by a statistician almost 100 years ago, where he basically explains that naturally occurring numbers usually start with a 1. So the first digit is usually a 1. And the second digit, and if the first digit is not a 1, it's probably a 2 or maybe a 3. Naturally occurring numbers hardly ever start with a 9. That's kind of an amazing thing, right? And what he did is he went around and looked for evidence of this. And this is kind of research 100 years ago. You open up a book, The American Men of Science, and then look for street addresses for the first people you see and figure out, okay, they usually start with a 1 and a 2, etc. And just to point out, since 1971, these books are called American Men and Women of Science. Right? And he also looked at physical constants, and again, this law held. And what we did is we looked at wiki tables, so all Wikipedia tables. And again, interestingly, on the right-hand side, you can see the expected count of first digits according to the law. And on the left-hand side, you can see what we actually observe. So you can see it follows quite closely this law. So if you just bundle up all the numbers that you find on Wikipedia, their first digit has this distribution. I think this is quite fascinating, and this is actually sometimes used as evidence in court in certain cases. Okay, so this is just single column profiling and a little bit of fun. Let's go more to the algorithmic parts. So let's go to the discovery of unique column combinations, so key candidates. So what are we looking for? We're looking for all minimal unique column combinations, meaning no pair of records has the same value combination if you project on that column combination. A key candidate, very simple. Just to give you one example, we looked at, again, this North Carolina voter data. We found one minimal unique column combination, which is the combination of voter registration number, zip code, and race code. So surprisingly, voter registration number alone will not identify a voter in this particular data set. You have to add the zip code and you have to add the race code to uniquely identify voters. This is just one example that we discovered, maybe a pointer towards poor data quality. And since we're looking for all column combinations, we will also find non-uniques. And this here is an overwhelming maximal non-unique. So this is saying if you put together all those columns, you still do not have a key. And keep in mind, it still includes the voter registration number. So again, this could be a data quality problem. Okay, so this already looks quite interesting. Unfortunately, it's also quite difficult. This is a chart showing the number of column combinations you have to look at. As I told you, this is an exponential in the size, as we know. If you look at the top right, you'll see that for 15 columns, you have to be looking at 32,000 candidates to validate whether they are unique or not. So running through the entire data. Of course, there are better algorithms. I'll show you one or two in just a second. One small remark, you might be wondering, why on earth would I be interested in a key candidate of size 15? Well, I just showed you some data quality issues, so why it's interesting, but I've also seen databases that actually do have keys of that size and foreign keys of that size. So this might be nothing that you show in a database class, but in the real world, you do have those kind of schemas. Okay, so how can we go about discovering these things reasonably? So usually we show the search space for data profiling in this lattice. This lattice contains all column combinations, and it's connected through the subset-superset relationship. And let's say we've discovered that the column combination AD is a unique column combination. So we're interested in these minimal uniques, and thus all supersets are also unique, but not minimal unique. So we can prune them away, right? If AD is unique, then of course ABD will also be unique, but we don't have to check that. So we can prune away large swaths of the search space. And it also works the other way around. So let's suppose we've checked a candidate, we found that it's not unique. So in this case, BCDE is not unique. There's a duplicate in there somewhere, right? So of course, then subsets of BCDE also cannot be unique. So again, you can prune away whole swaths of the search space if you go top down. Right? And this is exactly what algorithms do. So basically, you can approach this in an a priori with the a priori algorithm, exactly the a priori algorithm. You go level by level by level, and as you find minimal uniques / frequent item sets, right? You can, or non-frequent item sets in a sense, you can prune away everything that is above that particular node, and this works reasonably well. But of course, you can see the lattice does grow exponentially, so we're still stuck with this exponential problem in principle. I'll show you one idea that we developed a few years ago. Again, this is the same kind of lattice. By the way, this is the TPCD line item table or TPCH actually line item table. And we've also here marked the non-uniques and uniques, so you can see they're all over the place. And this particular algorithm does not go through the effort of going level by level by level. You can see there's a lot of work to be done until we hit the first uniques. But what this algorithm does, it goes depth first. So it starts at a random node and then just goes up, 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 up this lattice until it hits a spot where it's unique. And then it tries to follow that border that is a boundary between the uniques and non-uniques. So it kind of probes up and down the lattice at that level, and then thus separating apart the uniques and non-uniques. And this actually works very, very well. One kind of open research question, there is some work here, but kind of open, is how can we make these algorithms distributed? If you have a lot of data, can we distribute this? The problem, of course, here is the pruning. There's a lot of information that we need to share across nodes, because this pruning information can be discovered in any node, but is interesting for many other nodes. There is some work, for instance, again, by the colleagues in Waterloo on distributing profiling algorithms, but I would still argue there's still a lot to be done in effective distribution strategies for data profiling. Okay, this was for unique column combinations. Let's jump to the next topic, functional dependencies. I'm sure you all remember what a functional dependency is. So the standard example is zip code determines city, right? So when two tuples have the same value in the attribute set on the left-hand side, they must also have the same values in the attribute on the right-hand side, a functional dependency. And this definition implies a naive discovery approach, right? So for each column combination, you can extract one attribute, put it on the right-hand side, then you run through all pairs of tuples, check if the sameness holds. If it doesn't, you can break for that particular candidate and move to the next candidate. Of course, this is a catastrophe because you have something exponential, and then inside that exponential loop, you have a quadratic loop, so nothing you'd actually want to implement, right? And the search space actually, as you can see in this chart, grows even more than that of unique column combinations. So in this case, we have 245,000 attributes, candidates, because for each column combination, we can pull out each attribute and put it on the right-hand side, right? The nice thing is we can also show this search space in the same lattice. It's exactly the same lattice, but suddenly not the nodes are the candidates we're looking at, but the edges are the candidates we're looking at, right? If you look at the edge from AB to ABC, this basically is the candidate, does AB determine C, right? And then next to it, does AB determine E, et cetera, et cetera. So suddenly we have these candidates in this lattice, and the same kind of pruning works. So imagine you've discovered that A determines B, then we're no longer interested in whether AB determines C, because A alone already determines B, so AB together are not interesting for us. It's no longer minimal. So the kind of pruning up and down, of course, is different in nature, but the effect, in a sense, is the same. And again, there are a priori style algorithms that go level by level, significantly prune away the search space and come up in the end with all true functional dependencies. Okay? So many algorithms work that way. There's another way to look at this problem. This is, in a sense, a column-based algorithm, but there are also row-based algorithms. This is the F-Dep algorithm by Flach and Savnik. They don't look at this lattice and look at column combinations. Instead, they look at all pairs of rows. And for each pair, they check which functional dependency is violated by that row. Right? So you look at, for instance, the highlighted rows with Jasmine and Thomas towards the bottom, and they have the same surname, but different names, postcodes, etc. So you know surname cannot determine name, postcode, city, and mayor. Right? And if you look at all pairs, you know everything that cannot be true. And then through a process of cover inversion, you can come up with those functional dependencies that are left over, basically, that are then true. So this is a completely different kind of approach. It's quadratic in the number of rows, but it doesn't worry too much about the size of the schema. So we have two flavors of algorithms: a column efficient algorithm that's not very row efficient because it looks at all pairs of rows, and we have row efficient algorithms that look at column combinations and are very fast in checking candidates with nice index structures, but they have basically a different flavor. And I'll just present to you one quick idea of how to combine these algorithms to basically get best of both worlds. This is the HiFD algorithm that we presented at SIGMOD. It starts out on the left-hand side. It looks at pairs of rows. It looks at a sample of a pairs of rows. And for each pair, it figures out, okay, which functional dependencies are not true, which ones are true. And it just continues and continues until the efficiency of sampling gets low. So I'm not making many more discoveries as I continue sampling, right? The efficiency, I'm not gaining much anymore. So then we jump over to the right-hand side to the row efficient algorithm, but we get a head start because we've already discovered a whole bunch of things that are not true. So in a sense, we can jump ahead in this lattice and start higher up. And then we go through this lattice in a normal way, pruning, looking at candidates. And at some point, we're looking at candidates that where the validation efficiency is low. That is, we're not finding many new functional dependencies for each validation. So we're saying, actually, we think we need a little bit more data. And then we go back to the column efficient approach, and we go back and forth maybe 3, 4, up to 10 times or so until we're done with the algorithm, right? And this algorithm kind of adapts to the shape of the data and the shape of the schema. And it actually works quite well. So on the right-hand side, you can see, super great runtime. So I'm happy about that. But this chart is actually more interesting if you look at the bottom left, what I've circled, what kind of data sets we're looking at. So you can see we're looking at data sets with actually few rows. 1,000 rows is already kind of a large data set. And then you can see the number of dependencies where we're finding hundreds of thousands of dependencies in these small data sets. We'll get back to that problem later on. What can I actually do with these kind of results? Who's interested in 980,000 dependencies, right? Another interesting question, though, here is what is actually a useful and fair benchmark for data profiling? You can see these data sets have all kinds of different shapes, many rows, many columns. What is a good real-world benchmark for data profiling algorithms? I know of no work. In particular, can I generate data that tests data profiling algorithms? A very, very difficult proposition. Okay, so what can I do once I've discovered these functional dependencies? One quick thing that we've done, if you ask any student, any database student, what do I do with functional dependencies? Of course, it's normalization, right? In a sense, it sounds in our database classes like that's exactly why we're introducing functional dependencies, to show you what BCNF is, right? And actually, we can automate this a little bit. So given a data set, we discover all functional dependencies, we choose a key using some heuristics, we choose violating functional dependencies using some heuristics, and then we decompose with that violating functional dependency. And then we do this over and over until we're satisfied that all the decomposed tables are in BCNF, right? So it's a quite obvious approach. The trick is, of course, in choosing the right keys, choosing the right dependencies that we want to decompose on. And you can look at the paper to see what we do there. I do want to show you one result because it's kind of neat. Again, a TPCH, these are the 8 tables of TPCH. And we experimented in it by joining them all up into one humongous universal relation. So, with, I don't know, 100 attributes, huge data set. And then we ran our algorithm looking for functional dependencies, looking for keys, etc. And then we decomposed in the hope that what we get in the end is, again, the original TPCH schema, right? Because, it's well designed, let's say. And if you look at the results, this is kind of what happened, right? So we've color coded, and you can see, the colors really nicely match up to the original tables, with one interesting exception. If you look at the region table, the shipping priority in red kind of slipped into the region table. Why did that happen? Well, because there's a functional dependency. Region key determines the shipping priority. And maybe this shouldn't really happen in real world data, but in the benchmarking data, this is the case. So it's perfectly natural to put the shipping priority into the region if there's this dependency, right? So it's kind of neat that this worked out. One use case for functional dependencies: normalize your database. Okay. Moving on, last kind of dependency that I wanted to have a look at: inclusion dependencies. So inclusion dependencies are prerequisites for a foreign key, of course, right? And we look at unary inclusion dependencies and n-ary inclusion dependencies. Unary, just one attribute is involved. N-ary, multiple attributes are involved. So why is this interesting? This goes back to the use case I showed at the very beginning, integrating data sets. So at that time, we looked at bioinformatics data sets like the protein database or genome database, and they were shipped as many, many tables, but no foreign key constraints. So you just literally got hundreds of tables, and it's up to you what to do with them, right? They have keys, but they don't have foreign keys, right? And of course, if you look at web tables, it's even worse because there's no constraints, no keys, but still it might be interesting to see how do they join up. I just recently did a search. So this is a tweet by Daniel Pett, who was trying to make sense of the finds.org.uk database, which is about treasure finds in the UK. And you can see exactly what's going on here. Hundreds of tables and no connection between them. And a nightmare for us database people. But this is what we have to deal with sometimes. Okay, so why are they no foreign keys? Who knows, right? But lack of database knowledge, right? These are biologists, maybe. A lack of foreign key support in the database system at the time. Maybe they are database experts, but they think if I implement a foreign key, there might be a performance drop because the foreign key has to be checked all the time. And then also, of course, when you're integrating, obviously there's no foreign key between two separate databases, but there might be a reason to join them up. Okay, inclusion dependencies are a whole problem of their own. You can see this again in this chart about the number of candidates we need to check. This is humongous. It's basically exponential times factorial number of candidates. Why times factorial the number of columns? Because suddenly the order matters, right? There's a difference between ABC and BAC. It's a different kind of inclusion dependency. And so suddenly the search space grows very much. I won't show you any specific algorithm. We recently did a survey on some of these algorithms, and I'm only showing you this chart to show to you this is unary detection, this is n-ary detection, so large inclusion dependencies. How difficult this problem is. The left-hand side is minutes, so we're talking about hours, and it's easy to find a data set where you need days and days and days to find all inclusion dependencies, right? So I think this is this one area where we're still not quite there with efficient discovery of n-ary inclusion dependencies. It's one of the hardest problems in data profiling out there, okay? So one quick use case for web data integration, we applied this to millions of web tables to see, can we join up all the web tables somehow? Right, and this is a tool that we built at the time. The colored circles are basically clusters of tables that fit together that I can join up. Right, the thinking is if I then join up all those tables within one of those clusters, I get all the information about the entities in that cluster. So this example that I'm showing in the middle are tables that can join up based on the planets. Right, so Earth, Moon, Venus, well, Moon is not a planet, but still kind of slipped in there, Jupiter, Saturn, etc. And these are all kinds of web tables that have this column. If you join them all up, you know everything about planets, right? We didn't, we could only do anecdotal evaluation, but it actually worked pretty nicely. Okay. So as you can see, it's a very challenging research area. So in the remaining 10 minutes or so, I'd like to highlight some new directions. Where is the field going at the moment? What are more open research problems? What are further problems we're looking at? So, of course, there are other types of dependencies. I only mentioned a few. Obviously, if you open up any textbook, you'll find multi-valued dependencies, right, which are relevant for fourth normal forms or joint dependencies. There are denial constraints. There's all sorts of things. One thing I just wanted to quickly show are order dependencies. Actually, there's a paper at EDBT to discover order dependencies by some colleagues from Canada. And so an order dependency basically says if I order the table according to one column, it's automatically also ordered by another column. So if I order in this example here by salary, the persons are also ordered by their rank. Right? And why is this interesting? Again, you can use this in query optimization. So for instance, if you have an order by rank and salary, you can say, I might as well only order by salary, and I know it will also be ordered by rank, so I don't need to worry about that second order attribute. Again, doing the database system a favor. So this is for order dependencies. One, in my view, open research question is, how do I combine the discovery of these multiple dependency types? You already saw on the previous slides, they all have the same kind of pattern. I have a lattice, I go through the lattice, check candidates. They also often use similar data structures underneath. So a question is, can I run through this data and discover multiple kinds of things at the same time and not just have a specialized algorithm for one or the other? Now, that being said, order dependencies are a generalization of functional dependencies. Functional dependencies are a generalization of unique column combinations, but maybe we can slip inclusion dependencies in there. Maybe we can slip join dependencies in there. So we just have one, let's say, unified algorithm. Okay, next question is, what if the data changes? This is a significant research problem, and I would claim it's still quite open. There are a few approaches to handle this, but keep in mind that any change in the data can invalidate everything you've discovered so far, right? If you look at the database or the table on the bottom right, you'll see that first name, last name is a key in this table. But now imagine we enter a second John Doe. So suddenly first name, last name are not a key anymore. So we've invalidated that unique column combination. So we could remove it from our set of unique column combinations. The problem is, of course, there's a new minimal unique column combination, in this case, first name, last name, and city. So do we have to rerun the entire algorithm to rediscover them, or is there something a bit more intelligent I can do? Right? And this is true for any dependencies. So the open research question here is, can we efficiently maintain this metadata? Right? Especially important if I'm going to use it for query optimization databases. Databases change, and so I need to be certain that the dependencies I know about are still true. Okay, next open question, what if the data contains errors, right? We're detecting dependencies on a given data set, but we all know there are errors in the data set, so of course the dependencies we're discovering might also be erroneous. So there's a whole big research area on relaxed dependencies. On the right-hand side, this is a table from a survey by some colleagues that gathered all kinds of relaxed dependencies. So relaxed dependencies are maybe true only for a subset of the data. They might be conditional, so they're only true for US data, for US records, let's say. Or they can be matching dependencies, so we're relaxing the equality constraint. There's all sorts of ways to relax the definition of a dependency, and then there are all sorts of algorithms that try to discover them. And it goes further. There could be approximate algorithms in the sense that they can't even be sure that what they discovered is true, maybe because they're running on a sample. And then you could define dependencies on uncertain data or dependencies on incomplete data. This is an area that Sebastian Link is working a lot on. So a lot of fun to be had here. And then final big open question, that I get a lot, so I'm taking away your frequently asked questions maybe, but we can discuss this a little bit more, aren't what we're discovering arbitrary observations on one single instance, right? So for instance, if you look at the table on the right, we could conclude temperature must be a key or a unique column combination. But of course, this is a coincidence, right? It's not a good key. It just happens to be a unique column combination for this particular instance, right? And so can we find good features to identify keys among the unique column combinations? Big question. So can we make them genuine? Can we understand this is not just a coincidence? This should be true in general. Same is true for foreign keys. If you look at the two tables together now, you could conclude, sensor status must be a foreign key to customer status, right? Because all values of the sensor status are also included in the customer status. But of course, it's not an inclusion dependent. It's not a foreign key. It's a coincidence again, right? So the question we need to ask here is, can we effectively identify genuine dependencies among all the ones that we observe in a given instance? Big, big research question. And then we can branch out. And this kind of ties in to what Katja presented yesterday. For instance, can we apply data profiling methods to newer data models like RDF triples or graphs or XML data? And maybe what even is a unique column combination in an XML document? What even is a functional dependency in a graph, right? Or can we identify new kinds of metadata that are interesting there? So for a graph, we could think of node degrees and diameter and all these kind of other things. And the question is, can we efficiently profile for these kind of things? Right? The table on the right, or the figure on the right, we were trying to find what is a good key for a set of RDF triples, and we were looking for things that are quite unique and are also quite dense in the sense of we have many values. So the top right corner, those would be good key candidates, for instance, right? But RDF data often has this property that not everything is filled. You have a few facts here, a few facts there. So often enough, you don't really have a good attribute or good property that serves as a key. And we can go even further. We could do data profiling for multimedia data. So the figure on the right is some nice work by Daniel Keim and his student on well, he calls it literature fingerprinting. So it's textual data and extracting metadata about textual data. In this case, it's average sentence length. And the top row are novels by Jack London, and the bottom are novels by Mark Twain. And you can then see, okay, Jack London apparently has shorter average sentences than Mark Twain. And you can kind of, let's say, profile this textual data, extract metadata from it, and not just sentence length, but all sorts of things like parts of speech and other, let's say, linguistic measures you could be extracting, right? And then here, my question would be, what even are interesting metadata for multimedia, right? What is a functional dependency for a video? I don't know if that even makes sense, but I think this is worth thinking about. Okay, so I can come to the end of my talk. Obviously, this is all not my work, but that of my great students and great collaborators all over the world. And I do want to take this opportunity to highlight Thorsten Papenbrock, who is now a senior researcher. He'll be a professor soon in Marburg University. And much of what I've showed was done by him and together with his colleagues and myself. So really a great shout out to Thorsten. He's also the main contributor and author and developer of the Metanome framework, which is a framework and a collection of, I think, up to 40 or so different algorithms that we have at the moment for all sorts of data profiling tasks. So to summarize, what is the current focus? There are three big areas in my view. Currently, we're looking at efficiency. Can we make things even faster, more scalable? Semantics. Can we extract keys and foreign keys? What are good use cases for data profiling results? And we're, of course, looking at new kinds of problems like relaxed dependencies or new dependency types like, let's say, multi-value dependencies, order dependencies, etc. And they do translate into the future. So again, we still need to look at efficiency. That never goes away. As I said earlier, maybe distribution is an interesting part. Can we efficiently profile dynamic data, changing data? Can we maintain the metadata? Then for the semantics, I think this is still a great future topic. Can we extract or can we identify the genuineness? How can we use it for data cleaning? Of course, this is also ongoing, but I think there's a lot to be gained if we continue this line of research. And then, as I said just a minute ago, new problems for new data models, multimedia, graph, et cetera, et cetera. So with this, I'd like to close my talk. I hope I stayed in time, and I'm really looking forward to your questions now and then in the chats and meeting rooms later on. Thank you.
Okay,